Hello, Riles. For video 2.4, I want to take a look at the proof of the extended product rule. It came up, I think, once in the lesson. It's not really a rule that we need to use too often. And for its proof, I'm going to assume that the product rule is true because that proof doesn't happen until lesson 2.6. And then I want to just do a couple of other examples of the power of a function rule that we don't have a proof for in this course, but we really want to get the right language down so that we can transition into the chain rule easily. So first things first, if p of x is equal to f of x times g of x times h of x. Let's see if we can just construct this as a product of two functions. One function, that's a product of two functions, multiplied by some third function. So the product rule that we were told, that we sort of discovered works, is that the derivative of a product of two functions is given by the derivative of the first times the second plus the first times the derivative of the second. Notice how Leibniz notation is going to come in handy here, because I need to say I want to take the derivative of the first. I don't really have a notation here. You can't, and you also, like, prime of is not an operation. You can't prime things. So I'm going to do the derivative of the first times the second plus the first, f of x times g of x, multiplied by the derivative of the second. I'm not going to mess around with Leibniz notation here. I'm going to use Lagrange all the way. There's the derivative of the second, h prime of x. Good. And then all I need to do here is use the product rule right here. So inside here, to take the derivative of this product with respect to x, I'll do the derivative of the first, f prime of x, times the second, g of x, plus the first, f of x, times the derivative of the second, g prime of x, times h of x. And this actually suggests an alternative way of dealing with this extended product rule without actually using it, is you just use the product rule twice. Let's see, this is all just multiplication, so the brackets are not doing anything. I'm just going to write this as the first times the second times the derivative of the third. Let's try to get that in there. Yeah, that'll look nicer in my conclusion. Well, no guarantees. And then I think what I'm going to do here is just use the distributive property of multiplication through sums to say that this third is going to be multiplied by the derivative of the first and times the second. So I'm going to have the derivative of the first times the second times the third. And then I'm going to have the first times the derivative of the second times the third. F of x times g prime of x times h of x. And then here is the first times the second times the derivative of the third, h prime of x. There you go. Okay, so let's just take a look at the power of a function rule. Just another example or two of a function rule. And I think, you know what, we didn't really have any radical symbols here. Let's say if f of x is the square root of, let's just do x squared minus 5x. So I don't really have any alternatives here. I can't really expand this. This is a power of a function. Let's write it out as f of x is equal to x squared minus 5x to the exponent 1/2. And then I want you to visualize it as f of x being g of x to the exponent 1/2 if g of x is equal to x squared minus 5x. So let's go from sort of the function notation here, because this is closer to what our rule said, our formula said. F prime of x, you're going to take the derivative of the 1/2 power of something. That's going to be 1/2 times g of x, treating g of x as a variable. It's not 1/2 times g prime of x. You're not doing the derivative of the derivative of exponent negative 1/2. But notice, this is the derivative of f of x with respect to g of x, imagining that g of x is your variable. But g of x is itself a function on your variable. And for that reason, I need to complete what we call a chain. and multiply this by the derivative of g with respect to x. We may have had the opportunity to talk about applications in class where we say, imagine this is velocity with respect to temperature, and then we look at the rate of change of temperature with respect to time. Then we would say that the rate of change of velocity with respect to time is going to be the rate of change of temperature with respect to velocity times the rate of change. I've messed things up. I'm sure I explained it better in class. So we'll see when we get to applications. I think right now we should be able to just sort of trust it as a formula. Some sort of idea of taking let's try it in this way. Using the language of taking the derivative of the outside with respect to the inside times the derivative of the inside with respect to x. Oh, I know. I remember the example that we usually use. You've got an oil spill, and you could say that the area is a function of radius, but maybe your radius is a function of time. So we could say that the rate of change of area with respect to time is going to be the rate of change of area with respect to radius multiplied by the rate of change of radius with respect to time. We sort of convert between units or rates. We relate the rates. We create a chain between those variables. Let's try it here. The derivative of this function is going to be the derivative of the outside with respect to the inside. That's a little bit more generic. I think in this specific case, we could say it's the derivative of the power with respect to the base multiplied by the derivative of the base with respect to x. Derivative of the outside with respect to the inside times the derivative of the inside with respect to x is the general case of the chain rule. Derivative of the power with respect to your base multiplied by the derivative of your base with respect to x is the power of a function rule. Let's try writing that out in Leibniz notation. Derivative of f of x with respect to x is going to be the derivative of the power. Well, we want to get it eventually with respect to x. And what we do is we take the derivative of the power with respect to the base. I'm kind of mixing up my notations here. And we multiply that by the derivative of the base with respect to x. See, the delta doesn't really mean derivative of. It means small changes in, but it looks like a d, and so we often use that as a bit of a memory aid, thinking of it as the derivative of. Okay. So I suppose what I was doing here was I was saying that f prime of x is going to be the derivative of x squared minus 5x to the exponent 1/2 with respect to x, but I decide to create a conversion factor here. Okay, kind of like converting between, I don't know, kilometers per second by going kilometers per hour times how many hours per second. How am I going to take the derivative of this complicated expression, this power of a function with respect to x? By creating a link through its base, by creating a link through its inside. Okay, it's not a step I require you to show, but if you find it useful to have this written down, and then when you see this right here, that's what that is. And then this 2x minus 5, that's what that is right there. Then yeah, use this line. It's a special case of the chain rule. Okay. We handled manipulating this algebraically, and we'll get more practice with the algebra later. I wanted to focus more on the understanding.